Let's start recording. Okay. Hello, everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Professor Qing Lei. He's an associate professor at the School of Science in China, University of Geosciences in Beijing. He finished his PhD in computational mathematics from the School of Mathematical Science in Beijing Normal University. His research focuses on computational compressible fluid dynamics with particular emphasis on numerical methods for compressible multi-material flows, including the numerical simulation of interfacial physical processes and suppression of numerical instabilities at material interfaces. In his study of diffuse interface models, Dr. Lake has addressed critical challenges such as thermodynamic discontinuities at phase interfaces, non-physical oscillations, and shock interface interaction errors. He proposed innovative staggered projection methods for 7 equation models and energy splitting methods for 0 relaxation reduced models, significantly improving simulation accuracy. His work has been published in SCI journals such as a Journal of Computational Physics and Physics of Fluids. Professor Ching, thank you so much for your time today. With this short introduction, the floor is yours and you can start whenever you're ready.
Thank you, John. Everyone can ask questions when I'm doing reports. Now I begin my reports. My title is Asymptotic-Preserving Physical Informed Neural Network for Relaxation System of Conservation Law, Application to the Euler Equations. I'm Xin Lei, and this work is collaborated with Min Kang and Junfang Zhao. At first, I will introduce neural network and particle differential equations because my study is use neural network to solve particle differential equations. To give you a very simple neural network is a multi-layer perceptron. It's a type of artificial neural network. It consists of multiple layers of neurons. If you want to solve the neural network, you need to give some data to train it. If you want to solve a particular differential equation, the data, the input will be the space and the time, and the output will be the solution of the particular differential equations. So I will introduce the particular differential equations, and then I will go back to the neural network to explain more. What is particular differential equations? It consists of this form. There is a function f with a variable x1 to xn, and the function w, and the derivative of w. And if you want to solve this equation, you will get the solution of this equation. This equation is called particle differential equation, and the solution is W. I want to solve these equations, so to compare with the neural network, I will give you that what is input. The input is the space x and the time t. You will go to here. At first, input is x and t, and you will use the neural network to get the output. What is output? Output is the solution of the particle differential equation W. But if I want to solve a particle differential equation by the neural network, how to give an error measurement for the neural network. It means that I need to get a loss function. And if you want to solve a particle differential equation, not only the equation, but also you need to get the boundary condition and the initial condition. The boundary conditions means that you like like this kind of conditions. You know the all the time the solution of W on the boundary. And if you want to know the initial conditions, you will know at the initial time, means time equal to 0. At that time, you get the initial condition of the function W. To solve the particle differential equations, you know the boundary condition, initial condition, and the equations. All of this need to be satisfied, so we can get the loss function. It consists of the loss function of the particle differential equation and the loss function of boundary condition and the initial conditions. Why we choose this kind of loss function is it is the method of PINNs, the physical informed neural network. The loss functions here, if the loss functions approximate to 0, means the equation is satisfied. If the if this loss functions of boundary condition approximate to 0, means the boundary condition is satisfied, and the initial conditions also obey these rules. So to use a neural network to solve the particle differential equation, just to let the loss approximate to 0. It means that the goal of the neural network is to adjust the neural network, just adjust the weight of the neural network to minimize the loss function. We hope that it approximates to 0, and then we can get the result. The result is that we can use the neural network to form the solution of the particle differential equation. The solution of the particle differential equation just means that you give the space x and the time t, then you can get a solution. So in the neural network, you give space and time, and then you can get output is the solution. So this is the introduction of how to use neural network to solve particle differential equations. And then I will introduce the form of the equation that we solve. We solve this kind of equations called conservation law. This equation. These equations here, U is conservative variables, like some conservative variables like density or energy. Yeah, we have learned that it will be conservative. And Fu means flux. To solve this equation is a very typical hyperbolic particle differential equations. To solve these equations, it's very is sometimes difficult because there will be discontinuity in the solution of these equations. So how to solve these problems? We choose another way. We not solve this conservation law. We solve a relaxation system of the conservation law. Here is the relaxation system. Why we use this system? The reason you can see that here is a variable epsilon. Epsilon, if epsilon is very small, you will find is a very stiff term here. And if epsilon is very small, V will very quickly to equal to Fu. So if V is equal to Fu, and here this equation is just the conservation laws. So here the parameter epsilon is very important. If you let epsilon very small, you will find that V just Fu. And if you let the epsilon bigger, the V also will approximate to Fu, but it will take a long time. So this is the relaxation system. If we solve these equations, we have some we have something different between the conservation law and the relaxation system. The first thing is that we have more variables, not U, only U. We also have a variable V, but V not be forced to equal to Fu. So we have more freedom to solve the equations. More freedom if we use neural network to solve an equation. If we have more freedom, maybe it will be better. It will be easier to get a more exact solution. And the other thing is that then we will talk about the viscosity of hyperbolic conservation law. If we use relaxation system to solve the conservation law, we can add some viscosity. How big the viscosity is depends on how big the epsilon is. To explain it, we use the Chapman-Escort expansion in the relaxation system, and then we can get the first order approximation of the relaxation system. Now I just give you the result. The result is that to get the first order approximation, V is the first order approximation of Fu, and then the first order and the second order and the higher order term here. And then we take the first order approximation of V into substitute it into the first equation of the relaxation system. And then we ignore the higher order term. We ignore it means that we will let the epsilon not so big. We will let the epsilon be small. And then we can get that this equation, we take the form of V here, and then we can get the result of the relaxation system. Equivalent equation is this. It means that if we solve the relaxation system almost means we solve this equation to ignore high order term. This is this term now is adding term. So this equation is not equal to conservation law with this term because there are another term. This term almost is the second order derivative of U. So it's in physics or in numerical method, we call it viscosity.
Sorry, I have a question.
Okay.
Yeah, so what is A? A is F prime U?
A is a metric.
Which is the derivative of F with respect to U?
A is a metric, M-A-T-R-I-X. This metric to make sure that it will satisfy these equations. I will introduce later to satisfy these equations to make sure that the viscosity term is positive. You can give any metric A to satisfy this. We can use this equation. But if A is bigger, this viscosity will be bigger.
Okay, thank you.
And if epsilon is very small, the influence of A is not so big because epsilon is very small. We will very quickly to approximate to be equal to Fu. So you can think that the A will influence the viscosity, and A must satisfy this equation to make sure that the viscosity is positive. And then if we solve different kind of conservation law, like we solve Euler equations or we solve Burgers equations, we will choose different. We can choose different A to solve different equation. And if we even though we solve same equation, we just solve Euler equation, we also can choose different A. So if we use this equation, it just means that we can add some viscosity. It depends on how big epsilon and how big A. And this derivative and this process also can be generalized to high dimensional system of hyperbolic conservation law, like 2 or 3 dimensional conservation law. We write it in a very general form. This is 2 or 3D, 3-dimensional hyperbolic conservation law. And then we also can find the relaxations for the 2 or 3-dimensional system of conservation law. The form is very similar. And also, if epsilon is very small, it will Vi will be equal to Fi very quickly. So we also can get a form of this form. This form is that we solve these equations and we ignore high order term of epsilon. This equation is equivalent to this equation. This equation, and this is also viscosity. Also, you need to make sure that the metric A to satisfy this condition. This condition is called subcharacteristic condition. And we can prove that if epsilon is very small, if epsilon is approximate to zero, approach to zero, and this equation is just the conservation law. So you will find that the difference between F epsilon means the relaxation system. F epsilon means this, and F0 means the conservation law. F0 means the conservation law. So if epsilon is very small, approach to zero, and the difference of the conservation law and relaxation system is first order. So this result we will use later. So if we solve the relaxation system, the error, it just means that we solve the conservation law. The error is first order of epsilon. Now we can we use an example, use the two-dimensional Euler equation of gas dynamic to apply this method. This is the normal form of the two-order Euler equation. Rho is density, U and V is velocity, E is the total energy. To solve these equations, to close these equations, we need an equation of states. We use a very simple equation of state called gamma law to solve it. And then we can find the relaxation system of this conservation law. We write it in this form. I have introduced before. And here, the metric A, we choose this form, just other place. It is 0, just on. Sorry. And B is also this form, Why we use this form? Because if we choose A1, A2, A3, A4 with the characteristic of the Euler equation, we can prove that the sub-characteristic condition is satisfied. Also, another choice of metric A, we can use this A to the maximum of this variable. The metric B is similar. So we choose this form of A, we can get we can make sure that the sub-characteristic condition is satisfied. So is a good good choice of A. This method is this choose method is in Xinzhou and Jin's day paper. I just copy it here, use it. And then to solve, we can solve this equation instead of solve conservation law, the conservation law Euler equations. Why we choose to solve the relaxation system, not the conservation laws? Yeah, it's just an approximation, and the error is first order of epsilon. But why we choose this? At first, we can consider the traditional numerical method, like finite volume method. use this kind of method to solve the relaxation system. You not need a very difficult technique. You don't need to solve Riemann solver, or you also don't need to solve many nonlinear system of equations. So it's a very simple method. And even though it's a very simple method, it also can get a good enough result. And then the relaxation system approximate a viscous system of conservation law, not the conservation law, but of conservation law at a viscosity, at a viscous term. So it just means that you can use the relaxation system to add dissipative terms. And this term is associated with the relaxation rate, the variable epsilon. It's just like you can add artificial viscosity to numerical method to solve a conservation law. Why? A very traditional, a long time ago, people use this method, add some artificial viscosity in the numerical method to make sure that you can manage some numerical instability and prevent some unphysical oscillation near the solution, near the discontinuities, like shock wave or contact discontinuities. It's why we use this. We will take a very quick example later. It can smooth out discontinuity by add some diffusion. It just means add some artificial viscosity. A very simple example. We solve a very simple hyperbolic system called adventure equation. Solve the Riemann problem. It means that there is a discontinuity at x equal to 0. We use a very traditional numerical method, some traditional numerical method to solve it. You can find this example in Levick's textbook. It's a very traditional scheme, Lex-Fredensky scheme, first order, upwind scheme, first order, Lex-Van scheme, second order, Beam-Warming scheme, second order. You will find that use this first order scheme, you will find that it smooths out the discontinuity. And if you use high order scheme, the reason is that there are not enough viscosity, so there may be some oscillation. And to explain it, here also some oscillation. To explain it, why we need enough viscosity is that if we we use first order Lex-Fredensky scheme to solve the adventure equations, it means that in fact we solve the modified equations in this form, not the adventure equations. We add another term. In fact, we solve the equation with another term. This term is called viscosity term, with the second order derivative of U. This term is bigger enough, so you will see this phenomenon, the smooths out the discontinuity. But if we use the second order Lex-Van scheme, in fact, we solve the modified equation like this. This is the second order derivative, third order derivative. This term will will make some oscillation, and the viscosity is not bigger enough to present the oscillation to animate the oscillation. So you will find that there are oscillation. So if we use numerical scheme, in fact we solve this equation, not the not the hyperbolic equation itself. So it means that we need viscosity, and we use relaxation system. We can add viscosity into the conservation law. So it may be helpful for us to solve the relaxation system, because it can add some viscosity. So then I will introduce that I have introduced before how to use neural network to solve PDEs, particle differential equations. And in fact, we just use this method to solve the relaxation system, not the conservation law. And the initial condition is the same. When you need to add the initial conditions of U and V. V, you can add the FIU as the initial conditions. And the boundary conditions, it depends on which kind of boundary conditions you choose, like the Newman conditions or periodic conditions. All these many different kind of boundary condition you can choose is a very common method of pins to solve these equations. So to solve these three equations, to solve the initial conditions and the boundary conditions and the particle differential equations, we call the relaxation system. We can give the loss function of the neural network, just the loss function of particle differential equation, loss function of initial condition, loss function of boundary conditions. And then to solve this to minimize the loss functions, we can train a neural network to get a neural network to approximate the solution of the particle differential equations. And how to write these three terms? At first, we write the particle differential equation, just copy it here. And is a very common method to give many sample point in the computational domain, NR, numbers of the sampling point is NR. And then we calculate the L2 norm of the particle differential equations in different sampling points, and this is and these two equations is the relaxation system, and we add the initial conditions with the sampling point in the computational domain, and the boundary conditions with the sampling point on the boundary. And then we can give these three loss functions. And at this loss function here, we can get the total loss function. To minimize it, to train the neural network, we can get the result of the neural network to approximate the approximate the solution of the particle differential equation. This is the total progress of what I have said, to use the neural network to approximate the particle differential of the equation to minimize the loss function. If the loss function is not is very small, less than epsilon, a very small term, another epsilon, and then it is finished. If it is not not small enough, and we cycle this progress to use backpropagation method to update the weights of the neural network, and then to minimize the loss function. And in fact, we can add some data in this neural network to solve some problem like inverse problem. And I also have a simple example later of the inverse problem. This is what we will do in this progress of our research. And then I will use some mathematical proof to make sure that a good property of the relaxation system. And if I use neural network to solve it, we have a good properties. It's a very common properties called asymptotic-preserving properties of relaxation system. If you use numerical method, a traditional numerical method to solve conservation law by solve its relaxation system. What is asymptotic preserving property? I transfer it to the condition of neural network. It means that this F0 is the conservation law. F epsilon is a relaxation system. And if the epsilon approach to 0, F epsilon will approach to F0, means the relaxation system will approach to the conservation law in this picture. And then if the loss function approach to 0, we will get the result that the solution of minimize the loss function is will approach to the exact solution of the relaxation system, and the loss function approach to 0 also will get that the solution of using neural network to minimize the loss function will approach to the exact solution of the conservation law. And then epsilon approach to 0, under this condition, the loss function of the relaxation system will approach to loss function of conservation law. So why we need this asymptotic preserving properties, we call it AP properties, is that we need to make sure that the solution of relaxation will approach to the solution of conservation law. And we can use the neural network to the solution of neural network to approach the solution of the particle differential equation. So in fact, we need to prove this. We have improved this before. If you remember that the relaxation system is just to solve the relaxation system, just to solve the conservation law with an adding term called viscosity if we ignore a high order term of epsilon. So epsilon approach to 0, F epsilon approach to F0. And it's very easier to prove this. And we also prove this. And then we will introduce this at first. It means that the loss function of the relaxation system will approach to the loss function of the conservation law. It's the error is first order of epsilon. Why? It's very easy to find it, because this loss function, if we let epsilon approach to 0, epsilon equal to 0, no this term, and v will approach to fi, and then if we take fi here, it's just the conservation loss. So it's easier to approximate that if epsilon approach to 0, this loss functions is just if this loss function approach to 0, means the loss function of conservation law approach to 0. Just this term is 0, and this term is a first order term. So so we can get this result. It is just a very simple. You can. It's very easier to find it, and then we can prove that the if the loss function of the relaxation system approach to 0, you can get a result that the L infinity norm of this. What's this? This is the difference between the exact solution of the relaxation system, and this is the neural network result. Just a neural network to approximate the solution of the PDE. So if we can find that if the loss function converge to 0, you can find a sequence of the neural network, the result of neural network, to make sure that the convergence of the solution of the neural network approach to the exact solution of the relaxation system. So we prove it use some method like universal approximation theorem, and we ignore the progress of the proof. We just say I just say that we use some very important method like the Cauchy-Schwarz equality and the Gromwell equality. We can prove that. And after we prove that, we prove this cycle, this picture, these 4 parts we have proved. We ignore the proof here, and we just get the result. And then so, after that, I have proved the AP property. So it means that we have some convergence theorem of this method, the physical informed neural network method to solve relaxation system to approximate the solution of the conservation law. And then
Sorry, I have another question before you jump into the results. Can you go back to the last slide that you show, where you have the convergence? So can you go back one more? More? Can you go back? And more? I'm not interested in the proof, just yet here. So equation 29. So what is the index K here? When you say K infinity, what is K?
K is the index of the sequence. It means that I can use the use the universal approximate theorem. It means that you can find a neural network to approximate a continuous function Fourier measured function.
Okay, that's number of neurons then, I think.
So it means that I can use the neural network to approximate any continuous function.
Yeah.
This is a universal approximate theorem. Then use this method, use this theorem, I can prove that you can give me any function if it is continuous. If it is continuous here, if it is continuous, I can find a sequence of the neural network. This K means index of the sequence. To approximate it. But the reason the question is that difficulty is that I just can prove the result of continuous function because I use a universal approximation theorem. But the difficulty of conservation law is the discontinuity solution. I can't prove that, but I solve all the problem I solve is discontinuity problem with discontinuity solution. So this theorem is not good enough, but I just have this ability.
Thank you.
So it means that this four property when it is satisfied, I just prove that here and here, just the solution is continuous. I can prove it, but the problem that I want to solve is the solution with is the discontinuity solution. So this is a problem, but I can't solve it.
Hi, everybody.
Hello.
Hi, Bo.
And I will give you some result, some simple result to solve the short shock tube problem of the Euler equations. It's just a Riemann problem. The discontinuity is at x equal to 0.5. And the result is that here is a rarefaction wave, contact discontinuity, and a shock wave. I use the PIN method, the physical informed neural network method, to solve it, and use our AP PIN method to solve it. The AP PIN method is the red, and the PIN method is the blue one. The result is that you don't need to adjust the hyperparameter very carefully. You can get a good result if you use AP PIN. It just means that if you use the neural network to solve a relaxation system, not the conservation system, it's more easier to solve it. If you use the original PIN method to solve all the equation, it's more difficult. So you will find the result here, and solving and we have tested different epsilon. The red one is epsilon equal to 0, almost means no viscosity. And if epsilon is bigger, you will find that viscosity is bigger. It will smooth out the discontinuity here, smooth out the discontinuity. So if you use this method, you only also need to choose a good parameter epsilon, the value of epsilon. and it will not. It can't be too big. Too big means too artificial viscosity. Is not good enough. And epsilon also can't be too small. Some case it can't be too small, because too small means not good, not enough viscosity. And then we will present another test to show it. And we also solve inverse problem, just a shock tube problem. We solve it as inverse problem. It means that we don't know the specific heat rates in the equation of state, and but we give the data by use it equal to 1.5 to get some data, and use this data to solve a inverse problem to guess the value of the specific heat rate, and we can find that we can guess it very good, 1.5, and it's almost 1.5. Even though we add many noise, we can also get a good result. So this is we can in fact use PIN method to solve inverse problem is easier, but to solve the forward problem is difficult. Is more difficult, and this is another forward problem. A last problem, solve a Riemann problem with discontinuity at x equal to 0.5. And the result also can show that if we use the PIN method to solve the relaxation system is easier than if you use PIN method to solve. It's more difficult for you to solve it. You need a lot of time to adjust the hyperparameter. Maybe you also can't get a good result. And then we also test different epsilon. If epsilon is too big, you will find that the result is very bad. So we need the epsilon not too big. But the epsilon can be very small. This problem, we can find that epsilon can be very small, almost equal to 0, no problem. But we solve another problem called 1, 2, 3 problem, also a Riemann problem, with two rarefaction weight. The solution is that the 1, 2, 3 problem is that this is the solution. And if we use PIN method or use AP PIN method, it means that we use PIN method to solve Euler equation or relaxation equation. The result is similar. But if we use now we focus on the PIN method to solve relaxation system called AP PINs. If we adjust different epsilon, we will get different result. If epsilon is very small, you will find that is the green one. You will find that the result is not good enough, because I think that is not viscosity is not good enough. But we add some viscosity, the result will be better. And we add more viscosity, the solution will be not so exact, more error. It means that more viscosity means more error. So you also need to give a good relaxation rate. It just means give a good artificial viscosity. And we also solve some two-dimensional Riemann problems. It means that in 2D case, 2D computational domain with 4 different initial data, initial states, and then we can get the results of the result with time developing. We give we give 2 tests. This is the first test. We just see the result. The left is the result we solved by our PIN method to solve the relaxation system. The right is a very classical solution solved by stationary, a very traditional numerical method called the positive method, a numerical method to solve it. It's just a reference solution, and the left is the solution we obtain. You can find that it can solve it can solve it. I just can say that it can solve this problem. But if you want to get a better result, I think you need to do more. And then the next 2D Riemann problem. The left also is a reference solution obtained by numerical method. The left is the pin solution that we get. We also can say that at least the pin method can solve these two-dimensional equations. In fact, use pin method to solve 2D dimensional Riemann problem is not a very easy thing. This is all my numerical results, and I will give some conclusion. We give a PIN framework of neural network method to solve a relaxation system, incorporate the asymptotic preserving properties, and we have proved these properties. So it can enhance the ability of the neural network to solve discontinuity solutions like rarefaction wave, shock wave, or contact discontinuity in conservation law. It can also not only solve the inverse problem, but it also can solve forward problem. Forward problem is more difficult. And we have improved AP properties, and the result you can see that we can see some two-dimensional equation Riemann problem. We also get acceptable result. That's all of my presentation. Thank you.
Thank you so much, Ching. That was a really good presentation. Do we have any questions from the audience?
I have a couple of questions if nobody else has questions.
Please.
Okay.
Okay. So this is Ahmed from Brown. Thank you very much for your nice presentation. Very good research. So my question is that can we extend this to Navier-Stokes?
Okay, no problem. And we prepared to do it. Yeah. And we have done control method to control method control problem. We use this method can solve control problem of the conservation law with discontinuity solution, and we know how to use it to solve Navier-Stokes. It also can extend to Navier-Stokes. These papers, if you want to, what we want to do is follow a person's paper called Torwei-Chen. He teach me how to use the relaxation system to solve Navier-Stokes. So this method also can be extended to Navier-Stokes equation.
And then the second question is that, so you have that epsilon in your loss function, right? So during the training, can you set up a scheduler to just reduce epsilon value as you move on with the training? Have you done that?
I never done it.
Maybe that would help stabilizing the training and you can achieve lower values for epsilon.
In fact, it's very difficult to choose how big how big is the epsilon. It's not only the program for the research that I have done, but also for the traditional numerical method to solve relaxation system. How big you need to choose you need to set the value of epsilon is a difficult method. So I don't know how to set the value of epsilon, and is also not very easier to guess the value of epsilon. Like you can add the progress of guessing epsilon in the neural network is also very difficult. But another person told me a method I think is very interesting is that if epsilon is very big, is bigger, it means that it's easier to solve the relaxation system with discontinuity solution, because more viscosity you can get is easier to solve, but the solution is not so exact. But you can use this result to set as pre-train result, and use this pre-train result to adjust epsilon, to let epsilon smaller and smaller, and it maybe get a good result.
Thank you.
Great, thank you so much, Chin. I think that now we may need to move to our second talk, but this was a really nice presentation, so we are all grateful for your time.
Oh, thank you, Jen. Thank you very much.
Okay.
So now I close the sharing.
Yes, please. Thank you, Chin.
Thank you.
Bo and Zilin, are you in the call?
Yeah. Yes, Kwan.
Oh, great.
Yes, please, I'm here.
Thank you so much. Thank you so much for joining us. I think that is a bit later. Could you please try sharing your screen?
Yep. Let me share.
Great.
Works?
So now I'm going to introduce both of you and then you can start, okay?
Sure.
Okay, our second speaker, well, our second our second presentation today was going to be given by two speakers. Our first speaker is going to be Professor Bo Wan, who is a professor in the College of Mathematics and Statistics at Hunan Normal University in China. He received his PhD in Applied Mathematics from Hunan Normal University in 2011. From 2011 to 2013, he worked as a research fellow at the National University of Singapore, and from 2014 to 2016 at Nanyang Technological University in Singapore. He joined Hunan Normal University as an assistant professor in September of 2013. From 2018 to 2020, he conducted research as a fellow under the supervision of Professor Wei Tai at Southern Methodist University at the US. And currently, he's a visiting professor in the Department of Mathematics at SMU, continuing his collaboration with Professor Wei Tai. His primary research interests include the fast multifold methods in layer media and its application in computational electromagnetics, high-order numerical methods for wave scattering, machine learning algorithms for solving partial differential equations, and discontinuous Galerkin methods for PDEs. Also, we have a second speaker, and her name is Zilin You. She's a PhD candidate at Shanghai Jiaotong University, supervised by Professor Zhengli Xu and co-advised by Professor Wei Tsai at Southern Methodist University. Her research focuses on operator learning and fast algorithms for partial differential equations. Recently, she completed a manuscript titled MS-Scale FNO, Multi-Scale Fourier Neural Operator Learning for Oscillatory Functions and Wave Scattering Problems, which introduces a multi-scale approach for mitigating spectral bias in Fourier neural operators. Her broader research interests include scientific machine learning, computational mechanics, and numerical analysis. Bo and Zilin, thank you so much for your time today, and with this introduction, you can begin whenever you're ready.
Hello, everyone. Thank you, Wang, for the introduction and the invitation. My name is Wang. I'm from Hunan Normal University. I'm currently with Professor Kai in Southern Methodist University. This is actually my second time to give a talk in Professor Kanedak's group. So some of you may remember me. Today I'm going to give a joint talk with Zilin You from Shanghai Jiaotong University. This talk is about our recent attempt to mitigating spectral bias in operator learning. This talk has three parts. I will talk the first part and the multi-scale deep ONet in the second part. And Zilin will talk about the rest of them. The spectral bias is a well-known phenomenon in the DNN approximation, and in the DNN approximation algorithm, the approximation usually starts from the low frequency part and then gradually go to the high frequency part. You can see in this animation. This red line is the Fourier transform of the target function, and the blue line is the Fourier transform of the DNN approximation. You can see clearly the approximation starts from the low frequency region and then go to the high frequency region. This is actually quite different from the classic multi-grid method. You know, the multi-grid method actually first solve the high frequency part and then goes to the low frequency part. So there are some works that combine this the deep learning and the multi-grid method to take the advantage of both of them. One to handle the low frequency part and the other to handle the high frequency part. Actually, our group, there are several techniques proposed to mitigate the spectral bias, and our group worked on the multi-scale deep ONet, multi-scale deep neural network. It is quite easy. It can be quite easy to use in any architecture of neural network. The main idea of the multi-scale deep neural network is the spectrum scaling. Consider a high frequency function f. Suppose it is band limited, so the support of its Fourier transform is bounded in a domain B. This B is a ball in any dimension, and we define a scaled function f hat scale in the frequency domain. It's simply a scale of the Fourier transform of f. With this scaled function, we can take Fourier inverse Fourier transform, and we get expression for this fx by the scale f. So this scale f is just a scale function of f scale in the physical domain. But this f scale x its spectrum is bounded in a much smaller spherical, a much smaller ball. So this small ball is actually the scale of the original domain B. So it could be much smaller if you choose appropriate scaling factor alpha. So this scale function f scale x should be easier to approximate by a deep neural network. So we actually use a neural network to approximate this scaled function fx, and then you scale the neural network to obtain the approximation of fx. We don't need to mimic the whole process like this way. We just simply put some scaling factor in the DNA, in the input of a DNA, and then cleaning the network, we will the learning algorithm will automatically give you the approximation of fx. And we use the Professor Kai's group used this idea to solve an interface problem, a very complicated interface problem in 2D in this paper, and they can get very multi-scale deep neural network can catch the interface, the jump of the functions very accurately. In practice, we don't just use one scale. We usually use a multi-scale. This multi-scale comes from the domain decomposition in the frequency domain. So for the support of the Fourier transform of a target function f, this domain B, we decompose it into a set of hyperspherical annulars like this way. This AI, each AI is a spherical annulus in Rn. So we apply the spectrum scaling technique on each subdomain AI, and then combine the approximation together. We will have a multi-scale approximation for the target function fx in this form. So we have several neural network, and each of them has different scaling, have different scale input. So the architecture of a multi-scale neural network is quite simple. They just have several normal DNA, and each neural network, a subnetwork, you just give them a scaled input like this way. You have x and 2x, so this is scaled by 2 and scaled by n. So this scale factor are actually hyperparameters, and the number of scales is also hyperparameter. So you have to tune in different applications. We apply this idea to solve a Stokes flow in a complicated domain with oscillated solution. So you can see here the multi-scale neural network can improve the learning significantly, both for velocity and also both for velocity and pressure. Professor Kai and his collaborator from Boston University, they applied the multi-scale PIN to learn the effective dielectric of artificial material produced by putting a lot of scattering particles in a homogeneous background media, and and the multi-scale beam can learn the effective and homogenized dielectric constant like this. So these two figures is generated by a finite element method, and the mesh should resolve all these particles. So the computation cost is really high, and this is the result the classical finite element mesh produce. And this is the multi-scale pin. It's actually the pin used for both forward and backward, forward and inverse problem. They just use a multi-scale technique to handle the multi-frequency, the high-frequency nature in this problem. So this is the solution obtained by the multi-scale pin. We can see the accuracy is really high here. You cannot tell the difference of these two figures, okay? But the computation cost is much lower. They also use this algorithm to design a distribution of the particles to focus in the scattering in one specific direction. So they design this distribution of the particles, and so that the scattering field goes on the right-hand side. Okay, so what the energy of the scattering field, we are focusing on this area. We have last time actually I present the analysis of the of a two-layer multi-scale neural network in Professor Kanedak's group. I think it's last year. So we analyzed two layers multi-scale neural network under the infinite banded or infinite width limit. We show that the gradient descent learning of a regression problem is equivalent to a diffusion process in the frequency domain. So you observe the learning process in the frequency domain. It's actually a diffusion process. If the the learning rate goes to zero, the width of the neural network goes to infinity. And the architecture of the neural network will determine the diffusion coefficients. This A and B, these are diffusion coefficients. And we can show that the multi-scale neural network, actually the diffusion coefficient regarding the multi-scale neural network will have large support. So you can see this support will increase. The support will grow as this S goes to as this S increase. That means this eta actually is the area of the learning process. So this diffusion coefficients have larger support. That means the diffusion process will decrease the area in a wide frequency range. So that's why that explains why the multi-scale neural network can handle larger frequency range. I'm going to talk about our attempts on using the multi-scale technique in operator learning. Our goal is to learn the solution operator of a scattering problem, and also maybe it's inverse in the future. Okay, so the scattering problem is the scattering is due to the inhomogeneity of the media in a bounded domain omega. So we have inhomogeneity material in this in this bounded domain omega. And if you have an incident wave, it will generate a scattering wave. Okay, so this wave number k could be larger if you want to have a high resolution. So if you want to resolve the details of the inhomogeneous media, you have to send like high frequency incident wave, and then you solve the scattering problem. You may determine the this coefficient ax. So this in this problem, the right hand side f could be a external source, and it also can be the combination of the incident field and also the external force. And the scattering field should satisfy the radiation condition as x goes to infinity. We want to use the operator learning to learn the solution operator and maybe also the inverse of the solution operator. So the operator learning basically is it's a approximation in an infinite dimensional domain, but as an approximation, we actually transform the problem to a finite dimensional domain problem. So we sampling the target function, sampling the input function f on discrete points. So we have so this target function will be described to a vector f, and the neural operator takes the input of this vector f and also a given point, and then the output is a value in omega y. So this omega y could be a domain in another in the Euclidean space like Rn. So the dimension could be different with this x. In this talk, we only consider two architectures. The first is the deep overnet, and the second is FNO. I will focus on the deep overnet, and Zilin will introduce her work on FNO. So, how to see the how to consider the frequency in the operator learning? So, if we consider a simple example, this mapping is from an fx to sine 100 fx. So we sample the f on fixed sampling points x1, x2, x, and x, and the neural operator is giving takes the input of this vector f and also x. So this operator, the neural operator actually gives you a function z. This z could be this z is a function in very high dimension. It has input f1, f2, and mx, and also x. So the dimension is dx plus mx. But this is not the intrinsic dimension of d. Actually, this f1, f2, the mx, they are correlated, right? So the intrinsic dimension of d could not be that high, but we can see it as a function of the in this space. And if we consider this fx approximate by interpolation, maybe this phi I is the basis function, and then this neural operator, this mapping can have an approximation of this form. So we can see that our z function z should be an approximation of this one, of this sine 100 fi phi I x and take summation. So this z actually can be oscillate in this fi direction, and if I have many fi's, so this z could be highly oscillate along this fi, and also could be oscillate along x. So we have like two frequencies in this operator learning. One is on the X direction, and the other is on this input sampling points. So it could be really complicated. So our multi-scale deep O-net architecture is just as simple as we have done in multi-scale DNN. So in the deep O-net, we have a trunk net and a branch net. As we have shown that we can have high frequency, we can have highly oscillate components in X and F direction. So we generally put multi-scale technique on both this branch net and also the trunk net. So we have different scaling factors and the different scaling scales. So this ST is a scale of the trunk net, and this we will have an SB, which is the a number of scales in the branch net. This NT is the number of outputs of each trunk net. So this is the architecture of our multi-scale deep O-net. And for the trunk net, this T1, T2, TST, they are all vectors. They have multiple components. Okay, they take output from each scaled trunk net. But this branch net, the multi-scale branch net, this B1, B2, BST, they are all vectors, but they take inputs from all the branch net, all scales. So all the scales in the branch net will contribute to the output, and to each output of this branch net, and this branch net will times the output of the trunk net component wise, and we have this B0 for the zeroth order for the basis function of a constant. And for details of the branch net and this one is a trunk net. Sorry, this is a typo. This one is a trunk net. So the trunk net is stacked. We just stack all the outputs of the subnetworks, but in this branch net, this output will take all the contributions from all the subnetworks. Oh, so here is a simple example for nonlinear mapping. So we set this value equal to 30, and fx is taken of this form. This A, B, and C are random numbers generated in between like -1 to 1. So we use three architectures and deep O-net to learn in this mapping. And the first one is just the deep O-net. So we have scale. We don't have multiple scale in the branch and the trunk net. And the second, we have multi-scale in the trunk net, so 10 scales. And the third one, the third column, we have both multi-scale in branch net and trunk net. And we can see the first row is the performance on training data. We can see they all are learning the training data very, very, very good. But on testing data, only this we have a multi-scale on branch and trunk net. They have a satisfied prediction, and the other two they just cannot produce the reasonable prediction. And here is the number of parameters. The first one have parameters larger than the second row. But the third row the third column we have larger more number of parameters than the other two. Then tune this. Actually, we can still tune this network to use few parameters to produce making maybe similar results. And actually, the numerical experiments I will show next will not be consistent with this result. Sometimes we don't need this multi-scale in the branch net. We only need the multi-scale in the trunk net, and it will produce very good results. So we still have a lot of work to figure out what's the mechanism in these learning algorithms. Here is we consider a more complicated problem. So the mapping is given in this form. So this AM and BM are random numbers. We generated from a uniform distribution from -1 to 1 and fixed. And the input function is generated using this Fourier series actually. And this Fourier coefficients are randomly sampled from in a uniform distribution from -1 to 1. We put a scale factor C here to control the magnitude of these of the input functions. So this is the performance of the multi-scale deep O-net and the deep O-net compared in this in these two figures. This is the loss function. The green one is we use both multi-scale technique in branch and trunk net, and the yellow we only use a multi-scale technique in the trunk net, and this blue one no multi-scale technique used. Okay, on training data, the green one is the best, but okay, but on testing data, this yellow one is we only use a trunk net, multi-scale on trunk net. This yellow one is the best, and this multi you have both multi-scales in the branch and the trunk net. It's even worse than the original deep O-net. So maybe for this case we need to tune the parameters. So in this result, in this case, we choose m equals to 50. This is the numerical solution compared with the type function. Okay, the first the left hand side is on the okay, this the left hand side is on the training data. The left 4 pictures is on the training data, and the right 4 pictures on the testing data, and we can see the multi-scale deep O-net has performs a little bit better than the deep O-net, original deep O-net. So for this problem, now we consider a scattering problem. So this is a scattering problem. We write the scattering problem in this form. So this is the equation with respect to the only the scattering field, and the right hand side is given by the incident field. And this equation can be solved by a volume integral method. So we use this volume integral method to solve this problem, and the scattering field can be written as in form of this volume integral equation. So we solve this volume integral equation, and then generated the training data and the testing data. So this is only a one-dimensional problem. So the Green's function is given in this form. And this is the linear system. We use calculation method to discretize the volume integral equation and solve this solve a bunch of these linear systems to get the training data. So the input refraction index is generated as we have done in the in the test for the nonlinear mapping. So we use a Fourier series to generate the refraction index, and we put this scaling factor to make sure the magnitude of this perturbation and this refraction index is less than 1. Because in that equation, the refraction index is has to satisfy the magnitude has to be less than 1, so that the equation is still a homogeneous equation. And these parameters are randomly sampled in -1 to 1 with uniform distribution. Here is the training results. The left column is the loss on training data, and the right column is the loss on testing data. So we can see here on training data, the original deep O-net. So we test different cases of K, of wave number. So the first row is K equal to 10. The second row is K equal to 50. The last row is K equal to 100. So we can see on both on all cases, on training data, the multi-scale deep O-net with multi-scale on both branch and trunk net have better performance. But on testing data, basically only multi-scale technique on trunk net works better than other two architectures. So this is the solution. We predict using the multi-scale deep O-net. On the left part, this is the comparison of the exact solution and the prediction of the deep O-net on training data. So this is using a deep O-net. We can see this is the real part. This is the imaginary part. And okay, the first column is on training data. The second column is on test data. So this four figures is the result using generated using deep O-net, and the right hand side is the results generated using multi-scale deep O-net. So here we only use the multi-scale technique on the trunk net. We can see the original deep O-net cannot generate reasonable predictions for this high frequency problem, but the multi-scale deep O-net can achieve very good accuracy, even for this very high frequency problem. The third example we consider is an elliptic problem in high contrast material. So this is basically a 2-point bound value problem with a division boundary condition, and the high contrast material just leads to a very highly contrast coefficient AX. This AX actually is the modulus of the media of the material. So we model this material, the modulus of these materials by a summation of a bunch of Gaussian. This is a bunch of Gaussian. And this is the input of the modulus, example of the input of the modulus. We learn the stress, not the function of, not just the function. We learned not the function of the solution. We learned the derivative of the solution. So this derivative is actually the stress of the problem. So this is the how we generated the input data AX, and this is the training. We learned using multi-scale and also deep on-net, original deep on-net and multi-scale deep on-net. You can see this one, our multi-scale deep on-net have less number of parameters, but the prediction on both training and testing data is much better than the original deep on-net. Okay, so this is my presentation for the first part of this talk, and then now I will give this to the Zilin You, and she will present the next part of this talk. Thank you. Zilin,
Okay.
please share your presentation.
Okay. Thank you. Okay. Thanks, Professor Wang, for the introduction of the multi-scale dipolase. And now I will continue to introduce the multi-scale method applied on the FNO. Okay. Before focusing on the foreign operator, let's first look at the neural operator, which is the general architecture of operator learning. And the FNO is also built upon this framework. Okay, the primary goal of this neural operator is, of course, to learn mappings between two function spaces. And since we know that on computer, we can't handle the continuous function directly, so we need to do some discretization. So we will discretize the omega by sampling points x1 through xn, and usually in FNO we will just get a uniform grid, and for this will turn our problems from learning mappings between functions to learning mappings between vectors. Okay, and this sequence of the mappings is the process of neural operator, and these functions we can say they belongs to these function spaces. And we can see that they are all defined on the same vector space, that found on the same vector space, and the AX is a DA-dimensional vector value function, and VT is a dimensional, etc. And we can say that from the process has three main components. The first component is a lifting layer. The lifting layer is that when we given the input function x into the model, and they will use an operator denoted as P to map the input function x to a higher dimensional representation with 0x. And the divide here, the dimension is the dimensionality of the function VT. Okay, and this is like the channels. The definition of channels in the traditional neural network. And the purpose of the lifting is to make a network be able to learn and extract more diverse features. And this operator is usually implemented by a fully collected network. And we can, like this, we're using a matrix AP and a vector bias, a bias vector. And this matrix and vector are a parameter that we want to train. Okay. And the second part is components is this iterative layer. You can see from the V0 to V1 to VT. These are several iterative layers. And these layers will transform the VT minus 1 to the VTX. And each layer will include two parts. The first part is a local transformation. For example, we can using a matrix weight W to do a multiplication with the input of this layer. And another is a non-local integral operator with the curl function K5. And this integral will allow the information exchange across the whole domain. So these iterative layers will, after combining these two terms, we will apply combined with activation function. Usually we can use relu, glue, sine, cosine, such like that. And these iterative layers can both capture the local information by WT and a global information by the integral. And the last part is the projection operator, Q. This will map the last state, VT, X, to the output, UX. And there have many ways we can implement this operation, this operator. Usually we can use also use a MLP or just use a nonlinear mapping activation function and multiplied with combined with linear mapping like here. Okay, so this is the basic architecture of the neural operator. Okay, now let's see how the Fourier neural operator be designed by the neural operator. We know in the iterative layer we just introduced, there will have an integral, right? And there have a curl function. And in FNO, for FNO make assumption of translation invariance, which is said that the curl is only depends on the relative position between points. And with this assumption, we can use the convolutional theory from the Fourier analysis. As shown in the equation, the integral can be rewritten as such kind of formula in the Fourier domain. Is the inverse Fourier transform of the product of the Fourier transform of curl function and the Fourier transform of the VT minus, which is evaluated at X. And now we let the RT denote the Fourier transform of the curl function. Then we can rewrite the iterative layers as the last formula. Okay. And with this design, we are not learning the curl function in the real space. Instead, we can learn the curl function RT in the Fourier domain. Okay, it can be much more efficient because we can know if we get endpoint discretization and we want to calculate such integral in real space, is lead order a square complexity. But if we do such transition by switching the integral into the Fourier domain, we can only need a cosilinear complexity because the fast Fourier transform is only order n log n complexity, and the multiplication in the Fourier domain is order n complexity. Okay. And so here is the overall architecture of the Fourier neural operator. P is the leading layer, and the Fourier layer is the iterative layer that we had just talked about. And the last is the Q is the projection operator. Okay, And first, I want to point out important detail is that we can see the inputs. In addition to the input function x, we're also encoding the position into the architecture, right? Okay, this is very important. But the original FLO paper as shown here, they didn't discuss this in their paper, but they implement it in their code on GitHub. Okay, and this position is play a very crucial role in that when our solution target solution have some pattern that is independent of the AX. So then we have to have such a position input to make the architecture to learn some patterns that will solely depend on the position. For example, we can see the first example here. If UX is equals to sin AX, then our solution is totally depends on the input function X, right? So there is no need to add any additional input position into the architecture. So only the X as the input is fine. But if the UX, the operator have some other things, is that UX equals to sin AX plus sin X. Here the sin X is in the solution, but is independent of the input function. So in this case, we have to add the position as the input to make sure the architecture can learn something that only depends on the position. Okay, so we need to point out this because in later on we will design the multi-score method. We will consider both the two aspects of the input. Okay. And next, I will explain another very important mechanism in the FNO is the truncation mechanism of RT. We can say that in the FNO, we will do the integral in the Fourier domain, right? And when we in the Fourier domain, we will do fast Fourier transform of the Vt-1 function is the input of the each layer. And the Vt-1 function is a dimensional vector value function. And after discretization, it will be a dv by n matrix, right? Vt-1 will be a dv by n matrix. And after applying the FFT, the Fourier transform of the Vt-1 is also a dv by n matrix. And following that, we will do a multiply with the RT, multiplied it with RT is a tensor because we want to do some weight to do some weight on this. And instead of retaining all the n frequencies, we want to only retain the Kmax lowest frequency modes, and the Kmax is absolutely should less than n. This means that rather than needing a big tensor RT to multiply it with the Fourier transform of the Vt-1, we can only need a complex valued vector tensor with size of dv by Kmax. And the multiplication can be shown as this formula you can see here. For any fixed frequency, the multiplication will be a matrix will be a matrix and multiplied with a vector for any fixed frequency that is less than the Kmax. And when the the frequency is greater than the Kmax, there will be equals to 0. So with this mechanism, this step will help the architecture computing faster and significantly can reduce the parameter number, because the RT is what we want to learn. The RT is just the kernel function, is the Fourier transform of the kernel function. So it's what we want to learn. And when the RT becomes smaller, we need less parameter. Okay, next, we intend to apply the multi-scale method to the FNO. We propose an architecture that is very similar to the the deep neural multi-scale DNN that Professor Wang just introduced. The diagram shows the overall architecture. The idea is to use several parallel branches, and with each branch being a complete FNO. That means that each subnetwork is a FNO. But the only difference is that each branch will working with different scale inputs. So we can say in each branch they have different scaling inputs. That means we want to capture the different scale frequency information at different scales. Okay, and then the output from all these branches are then combined through a weighted sum to produce the final prediction UX. And we should notice that both the scaling factor and the weight gamma for the sum are all the parameters that we need to train. Okay, so it's very flexible. We can adapt it for some for more problems that is not fixed. So we don't need more knowledge of the problem. We can adapt it for that. And we also use activation function sigma x in all the Fourier layers using the sin x. Okay, now let's move on to our experiment, and this is our problem setting up. For the 1D problem, we will examine two architectures. The first is the normal FNO, and which has a single branch with 48 channels. And the second is the mass scale FNO with 8 branches, and each branch has 16 channels. Okay, and we use different channels numbers to ensure that both models will have similar number of parameters, because the mass scale will have more branches and normal only have one. So we only can adjust the channels number to make sure they have the same parameter. Okay, and also for one problem, we will employ one Fourier layer. It means only one iterative layer in each FNO, and we will retain the 500 Fourier modes. Here, the 500 Fourier modes is what we just said about the truncation. We will only retain the 5. Okay, sorry. We'll only retain the 5 lowest frequency modes. Okay, and for the 2D problem, it's similar. We will compare the normal FNO with single branch, but with 32 channels, and mass scale FNO with 8 branches, but only with 10 channels for each branch. And now let's see some promised results that I have done. Okay, this is first example. We studied a nonlinear mapping in the single frequency case, given by the UX equals to sin 30x, and x is belong to -1 to 1. An input function x is constructed as a summation of Fourier bases with random coefficients. Because we do such generating because it can approximate any continuous function within the same frequency range. Okay, and this picture profiles here is the profile of x and the discrete Fourier transform of x. And this figure shows that the testing error of mass scale FNO. And we can see the mass scale FNO quickly reaches the precision of order 10 to the -4. We can see have very high accuracy. But for this mapping, the normal FNO can hardly learn something. It always remains around the order 1. So this can actually, in other way, it can prove that this spectral bias exists in FNO. FNO can hardly learn some very high frequency mappings for the function between the functions. And this performance is further confirmed by the predicted solution. We can see in the right is the mass-scale FNO. Mass-scale FNO can accurately reproduces the detailed wave patterns of the true solution. And in the left is the long FNO. It can only roughly capture some information, and it is very less accurate as the mass-scale FNO. Okay, and next we will consider a more complex example. Is that the mapping is just a single frequency, is a multi-frequency example. We also generate the UX as a mixture of sine and cosine functions using Fourier basis. And M here represents the frequency modes with respect to the input function AX. And this will allow us to imitate any continuous mapping between AX and UX, okay? And this profile shows the DFT, the discrete Fourier transform of the solution under different value M. Okay, and this profile is showing the testing error of the different models during the training process on the different values of M. And we can see as M increases, we see a clear performance gap. There's a gap. You can see the gap become bigger and bigger. It can prove that when the M increases, which means the high frequencies increases, the information increases, the normal FNO, the performance become worse, and the mass-scale FNO is still perform very well. Okay, we can see for the M equals to 200, the mass-scale FNO can achieve accuracy of the order 10 to the minus 3. But the normal FNO can only stay at the order 1. Okay, and we can look at the predicted solution for the M equals to 200. This is the top panel. The top panel shows the predicted solution. And you can see that the normal FNO struggles to capture the rapid oscillations, while the FNO can be able to recover even the fine details. We can see the room inside. Okay, so it further shows that the mass-scale FNO have very promising, effect on this on capturing the high frequency information. And the bottom panel shows the discrete Fourier transform of the output from the different sublet work of the mass-scale FNO. We just said we designed 8 branches for the mass-scale FNO, right? And this is the 4 of them. And we can see with the smaller scale, they will tend to capture the lower frequency. And with the larger scale, they will tend to capture the higher frequency. Together, the multi-scale design can allow the multi-scale, can allow this model to reconstruct the entire spectral by the different scales, right? So it will be is a hierarchy architecture, I think. And this is a 2D problem, also for the nonlinear mapping, and the setting is similar as the 1D problem. So let's see some results for it. We can also see the result is that only with the 100 epochs, the normal FNO, the mass-scale FNO can drop to order 10 to the minus 2, and the normal FNO is hardly something. They only remains at order 1, and we can see the predicted solution here. In the left, the normal FNO can force to learn the oscillations. However, the mass-scale FNO learns very well. Okay. Next, we are going to present the example on the interior Helmholtz equation, and here we'll consider the mapping from the coefficients to the field. The coefficients is the x. X is the variable conductivity of the medium, and the ux is the denotes the scattered field. And we know for such kind of equation, for Helmholtz equation, when the coefficient Ax is a constant, we can rewrite the solution as by a green integral, right? By green function. And for different dimensional problems, the green function can list here. You can check. And now we'll consider a more complex situation that the A is variable. We first consider a 1D Helmholtz problem and varying spatial domains, because when the scattering scattering domain become bigger, it means the scattering size become bigger, and this will become more complex, and sometimes means more high frequency information on it. Okay, and here the omega we generate by this. Oh, sorry. Here is the omega. I write the A. Actually, here is the omega. This is omega. Okay, and we want to learn the mapping from the omega x to the ux, and all the solution obtained by using finite differential method. And this figure shows the characteristic solution of the 1D Helmholtz equation for different domain and sense. Okay, this profile shows that the testing error curves for different domain lenses L during training. And we can see across all the values of L, we can see that the masked models consistently achieves a lower relative error and faster convergence compared to the normal FNO. Especially for the L equals to 15, we can see the normal FNO has a very high error, right? But our method, the masked FNO, can also achieve a nearly order 10 to the -2 accuracy. And this slide compares the predicted solution and their frequency spectral. For the L equals to 15, we can see that on the top panel, the normal FNO can only roughly capture the smooth pattern, but you can see the rooming insight. But the masked method can very accurately capture the fine details and the high oscillations. And this can be proved by the spectral comparison. We can say in the normal FNO, the high frequency has low capture in the high frequency, but for the masked FNO, it's captured very well. And this example, we will consider the source term. And in the previous example, we will fix the source, right? We will only learn the medial omega to the solution ux. And now we want to make the source term as another variable input function to the model. And now we will consider the randomly generated fx by this. Here the di is random coefficient. And we will now learn the mapping from the omega f to the ux. And here we compare 3 models. The first is the normal FNO. We just input all these functions directly. And the second is the masked FNO1. We will add all the scaling factors. I add scaling factors on all the input functions. And the third is the masked FNO2. We will only add the scaling factor on the omega and the x, and the low adding on the f. We can say the result is that we can say the masked FNO2, which is the purple line, converges the much faster and achieves the lowest error. In contrast, the masked FNO1, the red line, the red line, performed even worse than the normal FNO, the yellow one. Okay, so it's indicating that the scaling factor on the source term actually decrease the model's performance. And this is actually match our theory, because we know in Helmholtz equation, the mapping between the source term and the solution is linear. So actually the mapping is a low frequency mapping. And if we when we doing some scale, adding some scaling factor on it, it will make it harder to learn the relationship between the two functions. So it will become worse. So this example I want to tell you is that there is less necessary for every function to add the scaling factor. We need to analyze the problem whether there exists some high frequency mapping. Okay, this is the Helmholtz 2D problem. Also says like the 1D, and the result is also similar like 1D. This is the input function and output function finger of the 2D problem, and they are all very, very high frequency information. And you can see here the top is the testing error curve of the different models. The normal FNO have low decrease, but the mass scale drops very quickly. And the bottom finger is the comparison of the prediction and the true solution. We can see that the normal can only learn a zero because they can't learn the oscillation, and they will only can learn an average value. So it's zero. But my mass scale is super good. And now this is the last part. We will introduce some results recently we have done on the inverse problem for Helmholtz equation. And we want to use the mass scale FNO and FNO to solve this. And we want to reconstruct the AX, the median here, from different software FK. And since mass scale FNO we know is better at handling some high frequency features, so we only focus on the median with very high frequency components. So we designed the median that we want to recover is like this. Okay, and we will generate some data sets under different FK. Is the solution the solution under different FK is U up versus K, and U up versus K is obtained by finite difference method. And here we also denote the capital GK is the solution operator for the source FK of the Helmholtz equation. And now we will address the inverse problem by iteratively optimizing with forward operator. And specifically, the first we will use a Fourier neural network A theta to construct or to initialize the AX, and then passing it into various forward operator GK. And GK we just said is corresponding to different source term FK to obtain solutions. And then the loss function is defined as the discrepancy between predicted solution and the true solution. And at last, we will using this loss to update the A theta. Okay, so what we do by our method is that we will use the multi-scale FNO and the FNO as a surrogate model to approximate the forward operator. And we need to train it. So this is the training data generated by this. And the FK we choose by this. Okay. And for each GK, for each forward operator, we will learn the mapping from the X to the UX. Okay, and these two profiles show the spectral profile and the profile of the media that we want to recover. And this slide compares the accuracy of FNO and muscular FNO when they are learning the solution operator for different source terms. They will be the surrogate model, right? So they need to learn the forward operator. This is their accuracy. We can say the muscular FNO has consistently better accuracy than the normal FNO. The normal is the blue and the muscular is the orange. And this is the reconstruction results of the two models. The left is the reconstruction result by the normal FNO. We can say that because the surrogate model by the FNO the accuracy is very low. So using FNO as the surrogate model to reconstruct the media is false. But use our muscular FNO because they can learn the forward operator very accurately, so they can reconstruct the media also very well. We can say for such so highly oscillations media, they can recover so well. Okay, this is the relative error between the reconstructed and the true media during training. The blue line is the blue curve is the normal FNO. It's always stay a high error, and our method muscular FNO when doing the reconstructing, it can be very quickly stabilized and drops sharply and at a very relatively low error level. Because actually the error is not very accuracy, but we can see from the photo is that as we say, it's good enough. Okay, and this is the last, I think is the last picture. We know in real applications, we can only observe parts of the domain, right? We can't observe the whole data. So this page will shows the reconstruction results with different observation intervals. And we can say in the red circle is the domain that we can observe, and the other is unobserved. We can say that in the observed region, the reconstruction matches the true media very well. But in the unobserved region, the accuracy drops. And we can see with the observation interval increases, the reconstruction in the unobserved region can improve. So in total, I think the key point for reconstruction is also data. We need more data to make reconstruct. Okay. Okay. Let me make a simple conclusion. Me and the Professor Wang, we both two have proposed two methods. One is the multi-scale deploy and another is multi-scale FNO. And both methods can address the spectral bias in active learning by scanning the input function. And we also designed a parallel architecture that can capture different frequency scales through various scaling factors. In our experiments results, we can see that even with fewer parameters, the muscular FNO and the deploy can achieve faster convergence and higher accuracy, especially on complex cases. And when I do the application on the Helmholtz equation, we found that with large scatterers, our method can successfully solve both the normal FNO and deploy struggles. Okay, and now let's just leave the reference up here for you to look at. And I'm very happy for you to ask any questions I can answer. Okay, thank you.
Thank you so much, Bo and Zilin. That was a really nice presentation. Do we have any questions from the audience? It looks like we do not have questions. So I guess that means that we can close the seminar. Thank you so much, Wang and Zilin. I think I mentioned that usually we post the recording on YouTube afterwards. You are both okay with that, right?
Yes.
Yes. Mm-hmm. Thank you, Huan.
Thank you both. I hope
Thank you.
Mhm.
Okay, bye.
Thank you everyone
you.
for your time. Have a good weekend.